static equilibrium. Let's start out by writing the condition of static equilibrium, and then we'll go on to problems. So from a content perspective, this is the simplest chapter because it can be summed up in 4 simple statements. First, that the net external force vector, that's super important, is equal to 0. Now, a corollary to that, that's saying that A COM vector is equal to 0. Those two say the same thing. And then V COM vector is equal to 0. Similarly, the sum of the torques vector is equal to 0. Right? Now I probably should say external torques as well. That means alpha is equal to 0. Notice that's not alpha COM, that's alpha about whatever the rotational axis is. And that means that A COM is equal to 0. So why is that important that I have all the vector signs? Well, even though this is one statement, folks, analytically it's 3, because that's net force along each of the spatial axes is equal to 0. Not just the net force is equal to 0, but each independently is equal to 0. That's just a convenient way to write it. Simultaneously, the net external torque is equal to 0. Why vector? Because there are multiple axes I could rotate about. I can rotate my pen about an axis down its barrel. I can rotate my pen about an axis that goes into and out of the page. And I can rotate my pen about an axis that goes into and out of me, right? Those are 3 perpendicular axes. And the net torque about all of those axes is equal to 0. So really, there are 6 conditions here that we've written as 2 conditions. And same here, v com x, v com y, v com z, or whatever it is the spatial system that you're using, a com x, a com y, a com z if you're using Cartesian, right? So there we go. Well, hold on, why is this? This should be, I'm sorry, this should be omega is equal to 0. So omega x, omega y, omega z is equal to 0. So it's not moving, and it's not going to change the way it's moving, so it never moves. Static equilibrium. So there you go. So let's look at the simplest problem, which is the seesaw problem. So let's take a uniform board, which will represent as a line. So it's uniform. So what does that mean again? That means that the linear density or the volume density of that thing is constant, and therefore the center of mass is located at the geographical center, right? We're going to be using that all through this unit. Obviously, we can, if we have non-uniform things, all we have to do is find out where the COM is using the calculus that we've learned before. But for now, we can integrate that in later. Ha ha ha, math joke. But for now, we're just going to keep this as uniform to make our lives a little bit simpler. So there we go. So there it is. So I've got a uniform board. Now the question is, where do I pivot it? Please do not make the error that the center of mass is the same thing as the pivot. The center of mass of this board is here at the geographical center of that object. So let's say the board is of length L. We know that the center of mass is L over 2 from either end, as long as it's uniform. But that doesn't mean I have to pivot it there. As we saw in the problem before, I can pivot my little seesaw system at the center, but we also saw what happens when I pivot it not at the center of mass. But because we're talking about a seesaw problem, seesaws are pivoted at the center, but don't think that pivot point is the same thing as COM. So notice here I'm using an X for the COM of the board. I'm going to use a triangle for the pivot point. So there's my pivot point. Okay, and I put 2 objects on here. So there's my lime